is the work which is connected with what Olivier Sobry told yesterday. So in fact, we are dealing with a sorting method à la électrotree. Yesterday, Olivier called this method erroneously MR sort, capacitive MR sort. In fact, it is a method which is, has been characterized by Denis and Thierry Marchand, which is called non-compensatory sorting methods or models, and which will be denoted in this talk NCS. So basically, the idea of such models is to assign an object to a category if the object is better than the lower limit profile of the category on a sufficiently strong subset of criteria, sufficiently strong coalition of criteria. And this is not the case when comparing the object to the upper limit profile of the category. So to be a little bit more precise, the ingredients of such model are the following. So you have, in the simplest case, only two categories, let's say the good and the bad. The objects to be sorted are described as vectors of performance vector which belong to a Cartesian product of attribute or criteria scales, which are ordered. And there is a limit profile, which is itself a vector of this subset, of this Cartesian product. And then there is a family of sufficient coalitions, that is a family of selected subsets of the power set of the set of criteria, which is upclosed by inclusion, which means that if a coalition is sufficient, any coalition that contains it is also sufficient. And so the assignment rule works as follows. You assign X to the category of good alternatives if the set of criteria on which X is above the profile belongs to the family of sufficient coalitions. So if the X beats the profiles on a sufficiently strong coalition, what is sufficient is determined by belonging to this family. So of course, particular case is the MR sort model, in which F can be determined by weights and a threshold. Then, if the model is a degraded version of the NCS model, the assignment rule works as follows. X is assigned to the good. In fact, it's not the bad, it's the good. But in French, good is bon. So if the sum of the weights of the criteria on which X beats the profile passes some threshold lambda. Okay. So yesterday, Olivier gave examples of rules that can be described in the MR sort model with exams and things like that. This is an example in which it is possible to represent the rule by the MR sort model, by weights and threshold. And this is another example in which it is not possible. Basically, it's the same as was shown yesterday. If the rule is that to be successful in your examinations, you have to reach a mark of at least 12 on one of these two subjects and one of these two subjects at least, this is a rule which is not representable by weights and threshold because, in fact, you have contradictory constraints. You have that here, if you number these 1, 2, 3, 4, then you have W1 plus W3 must be larger than lambda to to succeed, or this, or this, or this. And these ones are not sufficient because here you are good in French and English, but it's not enough. And you are bad in mathematics and physics, so it's not enough. So this system of inequalities has no solution, so it's not representable in the Emersort model, but it is representable in the NCS model because a family of sufficient coalitions are the following. So French and mathematics is a sufficient coalition. English and mathematics is a sufficient coalition. And there are some dots here because I only wrote the minimal sufficient coalitions. Of course, if you are good in all 4 subjects, you will also succeed. Okay. So the question we are interested in is to what extent the NCS model is more general than the Emersort model, is more expressive, let's say. So one way of putting this question is to ask which upper sets, so which families of sufficient coalitions can be represented by weights and threshold. So one way of checking if a given rule can be represented is by linear programming, for instance, by solving this kind of linear program. You have to formulate the constraints by listing the minimal sufficient coalitions and the maximal insufficient coalitions and say that these are the constraints related to the minimal sufficient coalitions, and these are the constraints related to the maximal insufficient coalitions. So, okay, there are, of course, other means of checking this. In fact, the problem is, in fact, that the minimal sufficient coalitions form an anti-chain in the ordered set of the parts of the subsets of the set of criteria, which is ordered by the inclusion. So the minimal sufficient coalitions are an anti-chain, that is a set of subsets such that none of them is included in another. Okay? So, and there is, of course, a one-to-one correspondence between upper sets and anti-chains in this set. So you can either describe the set of sufficient coalitions by listing all of them or listing the lower limit, let's say, of this subset that is an anti-chain. So a subset of subsets that are not included in one another. So we can reformulate the problem like this. For each anti-chain, test whether it is representable by an Emersort model. Of course, this is a well-known problem, and it's also difficult by the number of anti-chains. So the number of anti-chains is the Dedekind numbers. It's a Dedekind number. It's a famous integer sequence, which is rather short, or at least the elements that are known are not very numerous because D9 is not known. It is known that it has more than 42 digits. Yes?
May I ask just for clarification?
Yes?
On the previous slide, you said given an anti-chain, check whether it can be represented.
Yes.
Okay. Now you say for n is equal to 7, there are many anti-chains.
Yes.
That's a different point, right? I mean, if you give me one anti-chain with n is equal to 7,
of course, you can check.
I don't care.
But here we want to examine the question in all the set of possible rules or anti-chains, which one are representable? So one way, brute force way of checking that is to solve as many linear programs as there are anti-chains. I know it's closely related with Boolean functions and other, and I come to this. This is not a possible way of doing things because if you want to check every every anti-chain, for instance, for n equals 7. If one anti-chain takes 1 second for checking, then you will need more than 70,000 years to check everything. And even if it takes 1/100th of a second, it's already too much. So of course, this question arises in many other contexts, as Andre and you said yesterday. The Dedekind numbers are also the number of monotone Boolean functions of n variables. In cooperative game theory, it's also the number of simple games. And so our problem, if we suppose that the profile is fixed, so NCS model is more than just those rules. You have also to fix the profile in general. But if the profile is fixed, and here we are interested in this, we suppose the profile is fixed, and we examine the rules. So the rules with the fixed profile which are used here are, in fact, in bijection with monotone Boolean functions and with simple games. The sufficient coalitions are the true points, and the winning coalitions of players in simple games. And in the degraded version, this corresponds to threshold functions in Boolean function, or with weighted majority games with quota in game theory. So this question has been addressed at least in the two other areas. And many papers study this question. For instance, there are characterization results in the context of Boolean functions. There are study of subclasses of simple games, and also the weighted majority games, that is the MR-sort rules, have been listed up to n equals 7. So in fact, I should not say one word more, except that, in fact, we want to study particular classes of rules that are in between MR-sort and the general NCS class. And also, we want to have a list of all the anti-chains in order to be able to simulate random sampling, let's say, of NCS model. I just give an explanation of this. So the first issue, other classes, which classes? In fact, any NCS rule given the profile can be represented by not a set of weights and a threshold, but a capacity and a threshold. So a capacity is a non-additive measure, not necessarily additive measure, and in general, you can represent it like this. If you use the Möbius interaction function, so the measure of a coalition, a set of criteria, a set of players, is the sum of the weights assigned to each player plus the sum of the weights of the pairs, the interaction, the pure interaction between players, two players, plus the sum of the interaction, pure interaction between three players, and so on. And so a k-additive capacity is a capacity where you just need to go up to k tuples of players or criteria, and not over it in order to represent the rule. So one additive capacity is just when you have this, and it's a weighted, it's using weights. A two additive capacity is when you go up to this point, and so on. So the classes in which we are interested is which NCS rules can be represented by one additive, but it's MR-sort, two additive, three additive, and so on. Perhaps these are it's a question that has been studied in other fields, but we are not aware of it. So the simulation issue, what is it? So we are interested in learning this kind of models. And so if we devise a method for learning NCS model, capacitive MR-sort model, for instance, we want to test this method, if it works. And one way, a basic requirement would be that if the learning set, artificial learning set, has been assigned by a NCS rule, then the learning method should be able to retrieve it at least approximately. Okay? So in order to test that, one way of doing it is select an NCS model at random, use it to generate a learning set, and then, generate objects that will constitute the learning set, assign these objects by the known model, and then test the learning model. So, but the question is, how shall we select a representative NCS model, one and several, in fact? How shall we sample the space or the set of NCS models? One way, for instance, would be to generate a capacity at random, but this is not clear what it means. So one other way is to be more intrinsic and select one rule, one anti-chain at random. Okay? So for that, one way of doing it is to list all of them. So what we have done is something very simple, which is to list all the anti-chains up to n equal to 6 and to classify them into two additively representable, one additively representable, more than two additively representable. Just to have an idea, in fact, and to be able to simulate at least in simple cases. So it's complicated, so there are many, even for n equals 6, so we need to save time. So we can restrict to non-equivalent families of MSC, that's minimal sufficient coalition. So in the case of n equal to 4, for instance, those three, so this is an anti-chain or a set of minimal sufficient coalitions. This one is equivalent because it's just obtained by permutation of the labels. So if one is representable by a given model, the other is representable by the same type of model. So, so we can only test things on non-equivalent family anti-chains, let's say, and the number of inequivalent anti-chains is also something which is known, but R7, the case for n equal to 7, has been only recently computed by Stefan and Yusun, and it's this amount. So it's still too big to list. So we restrict our ambition to n equal to 6. So how shall we list all these things? So the classical idea is to list first the different types of anti-chains. So the type of anti-chain can be described by a vector in which you just state how many coalitions of size I there are in the anti-chains. So for instance, the type of this anti-chain is 0, 4, 4, 0, 0 because there are 4 pairs. And the type of this one, there is 1 pair and 2 triples, is 0, 1, 2, 0. Of course, not all types are possible. One restriction is, for instance, the fact that the maximal size of an anti-chain, maximum number of minimal coalitions is the Sperner number, which is this. And so for n equal to 3, the sum of the case in the type is maximal, is less or equal to 3, and for n equal to 4, it's less or equal to 6. So for each type, each feasible type, we generate all possible anti-chains and we discard the equivalent ones, but we count them because we want to know which is their frequency. Okay, so in the case of n equal to 3, we have this picture. So for instance, here you have in type 200, there is one representative, which is this one, but if you permute the labels, you have also 1, 3, and 2, 3. So you have 3 representatives, 3 members in this equivalence class. Okay, so in total we have 8 inequivalent and 18 in total, plus 2 trivial cases, which are not very interesting. So we can still, to list things, we can also use some other savings, which I skip. So for the list of inequivalent anti-chains for n equal to 4, we have this picture. So you see, for some types, you have non-isomorphic anti-chains. For instance, here with 2 pairs, we have here 2 disjoint pairs for n equals 4. So there are 12, sorry, no, disjoint pairs are here. You have 3 copies of this. And you have also pairs which have a common, which have an intersection, and there are 12 such anti-chains. Okay, so here is the complete list. You find here the anti-chains that were considered in the initial example for succeeding in exams. There are 3 copies. Okay, so now we try to classify all these anti-chains, and we do that up to n equal to 6. So C2 is, in the column C2, we list the number and the percentage of inequivalent families that can be represented by a 2 additive capacity, but not by a 1 additive, that is by a Emersort rule. And C3 is the same thing for 3 additive, but not 2 additive. And so we see that up to n equal to 3, you just need Emersort. It's enough, and it's well known also in game theory, for instance. From 4, you need some 2 additive. And here is we had an example initially, and there are 2 other examples. Sorry. So it makes 10% of the total of inequivalent families. We don't need C3 up to n equal to 6. And then for n equal to 6, there is a substantial amount of rules that cannot be represented by weights and threshold. And there are few of them that cannot be represented by 2 additive capacities. So we can do the same for when we consider the multiplicity of the inequivalent anti-chains. The picture is roughly the same with a little bit more non-one additive representable thing. Okay, so the comments are the following. The expressivity gaps, the gap between the 2 models seems to grow very quickly with n. Another observation is the 2 additive capacity is enough up to n equal to 5. And we have a list that allows us to sample examples of NCS model uniformly at random in some sense, in some sensible sense. So there are 2 possible ways of doing. Either you sample by giving equal probabilities to all inequivalent chains, or you weight these inequivalent chains by their frequency. So we can do that up to n equals 6 with methods that can be improved, of course. But yet doing it for n equals 7 is not easy. Note that the problem of sampling MR-sort rules is also not very well solved, because usually for sampling those models, one samples sets of weights in the simplex and the threshold, and this induces some sort of distribution on all those rules, which is not necessarily very convincing. Okay. Now, for concluding, I have some more questions. So one question is, do you know of studies about these classes of models or of Boolean functions or games studied in the other areas? Another question is there a way of sampling anti-chains in a representative way without listing them, because it's not possible very soon? And then another question is, in fact, is it so sure that the expressivity gap between the two models is so large? And I come back to something that was presented yesterday by Olivier, but which did not raise any remark. So yesterday, Olivier has explained that in order to test the difference of expressivity, he has generated, well, all Boolean vectors of n variables, assign them using an NCS rule that is not an MR-sort rule, and then learn a MR-sort model minimizing the number of wrong assignments. So here we are not trying to reproduce exactly the rule, but approximating, in fact, as good as possible. And he showed this thing. So he showed that, in fact, the number of not correctly assigned vectors is not very bad. Is not bad. So the linear rule, the MR-sort rule, gives a good approximation, in fact, of the NCS rule in most of the cases. So in average, for n equal to 6, when you have the true rule is not a one additive one, you can represent most of the vectors, except for 3/64, by a linear rule. So maybe the gap is not so big if you consider approximations. So thank you.